Before we start talking about our newest rule, the chain rule, I do just want you to think back to the past lesson on composite functions. So recall that the composition of two functions, f and g, can be defined by, so we have two ways to write this. Y is equal to f of g of x, and the second one you would say it the exact same way. Y is equal to f of g of x, so that little circle right there is of. Some of your teachers may have said that this is called fog. Either way, it means the exact same thing. The one main thing I do want you to remember as we move forward is that the innermost function, so in this case the g of x, is what we are going to replace for x in our f of x function because it is the inside function. So we're just going to go through a couple of examples here. So if we have f of x equals x squared plus 2x and g of x equals 3x minus 4, then number one, determine f of g of x. So when I look at this, my inner function is my g of x. So what I'm going to be doing is I'm going to be replacing all of the x's in my f of x with 3x minus 4. So f of 3x minus 4. So what I'm going to be getting is 3x minus 4 squared plus 2 times 3x minus 4. Now if I go ahead and simplify all of that, I'm not going to do it the long way for you. I'm just going to go ahead and do this. I'm going to be getting 9x squared minus 24x plus 16 plus 6x minus 8. And then finally, I'm going to have 9x squared minus 18x plus 8. In the second example, it is the exact opposite. So this time, I'm going to be plugging my f of x, so my x squared plus 2x, in my g of x function. So g of x squared plus 2x. So that is going to equal 3 times x squared plus 2x minus 4. So 3x squared plus 6x minus 4. So looking at these two examples, I'm going to ask you, does f of g of x equal g of f of x? And I'm sure you can see by this counterexample that we just did, no, it absolutely does not. So moving forward, we do need to be careful about which functions we're calling our inner functions and which functions we're calling our outer functions. So before moving on with our actual chain rule, I did just want to give you a quick recall. So the derivative of y equals f of x is equal to y prime, or dy by dx, which means the derivative of y with respect to x. Suppose you have y is equal to 5 minus 3x to the 4 plus 3 times 5 minus 3x squared. How could you find dy by dx? So the first thing that I notice right away, obviously, I could expand this out. It would get ugly, it would get long, it would get messy, so I'm not going to do that. But I do see that what I have in both of these brackets is the exact same. So I'm going to go ahead and I'm going to say, let's let u equal 5 minus 3x. Now, if I do this, then I can say that y is equal to u to the 4 plus 3u squared. This definitely looks a lot easier to calculate the derivative of. Now I'm going to go ahead and I'm going to find the derivative. Now here I'm going to have dy by, normally I would write dx. There are no x's in this equation though, so I have u's. I'm going to have to say dy by du. Now we know that this is equal to 4u cubed plus 6u. Now I can't forget that I let u equal 5 minus 3x. So if I go over here and I do du, so the derivative of u with respect to x, because I have x's in here, I am going to get negative 3. If you think back to our end goal was to find dy by dx. Now, I wasn't able to do that, well, I was, but it would have been long and messy. I decided to do it a different way. I decided to use u. So I need to somehow make up this chain where I start with y and I end with a dx, but I've used this du in the middle. So if I go ahead and I plug a du in here, what I can see is that this du and this du would cancel each other out, and I would be left with my dy by dx. But in the meantime, I needed dy by du, which I found, and I needed du by dx, which I also found. So now that I've created this chain to get me to my final answer, I can go ahead and I can plug that information in. So my dy by du was 4u cubed plus 6u, and my dy by dx was negative 3. So if I go ahead and I multiply this through, I'm going to be getting a negative 12u cubed minus 18u. And then what we need to do, or what we have left to do, is take this u equals 5 minus 3x and plug this back in. So negative 5 minus 3x cubed minus 18 times 5 minus 3x. Since I'm not asking you to do anything with this, I'm just asking you to find the derivative. I am okay with you not simplifying it, so we're just going to leave it at this point. So just to make things a little more tidy, if y is equal to f of g of x and u is equal to g of x, then dy by dx is equal to dy by du times du by dx. Or if f of x is differentiable and y is equal to that differentiable function to the power p, then the derivative is equal to p, so bring that power down, times my function to the exponent p minus 1, so this is the same as normal. All of that needs to be multiplied by the derivative of that inner function. So we are going to go through a couple examples. This first one says find the derivative of the following. Now, what I notice right away is that I have the exact same thing here. That gives me the idea that it is going to be easiest for me to let u equal the 5x minus root x. Now, this allows me to say that I have y is equal to u cubed minus the square root of u. Now, I know that since I am substituting a u in here, I'm going to be using my Leibniz notation. So dy by dx is equal to dy by du times du by dx. And I can go ahead and find this information. So looking at this, the first thing that I need to find is my dy by du. So I'm going to go over here to my y equals 3u squared minus 1/2 u to the negative 1/2. And I'm not going to worry too much about my negative exponents. I'll deal with those later. So I'm going to go ahead and plug this in here. That's an equal sign. And the next thing that I'm going to be looking to do is my du by dx. So I'm going to go up here, and it's going to be really tight because I can't move it. 5 minus 1/2 x to the negative 1/2. So I'm going to go ahead and I'm going to plug that du by dx in here. And then on the next line, I'm just going to go ahead and I'm going to tidy things up a little bit. So 3u squared minus 1 over 2 root u, 5 minus 1 over 2 root x. Now at this point, I can go ahead and make that final replacement. So plugging in this u and then get my final answer. So I went ahead and I plugged in my u is equal to 5x minus root x every single time I saw u, and I got this. Now there's no way that I would ask you to reduce this any further, and this is where we would stop. In this example number 2, I'm giving you 3 equations or 3 expressions, and I'm asking you to find dy by dx. And how we're going to do that is we're going to have dy by du, so we're going to derive our y with respect to u, and then we're going to derive our u with respect to v, and then we're going to derive our v with respect to x. And when I look at this, I will get dy by dx because I've got these du's canceling and these dv's canceling. So now I can go ahead and just plug my derivatives in. So dy by du is 20u cubed minus 1 My du by dv is 2v, and my dv by dx is just 3. Now at this point I do need to go ahead and replace my u and my v with the equations above. So I will be getting 20 u cubed, so it's actually v squared cubed, so v to the 6 minus 1 times 2v. My v is 3x plus 1, so when I multiply by 2 I'm going to get 6x plus 2 times 3. Now I'm almost done. I need only x's in this equation, so I do need to go ahead and replace this v with my equation for v. So I'm going to have 20 times 3x plus 1. Sorry, that's really messy there. To the 6 minus 1 times 6x plus 2 times 3. Now I'm going to go ahead and I'm just going to multiply this 3 in here just so that it looks a little bit nicer. X plus 1 to the 6 minus 1 times 18x plus 6. My derivative at this point is done. I'm not going to expect you to go any further than this. For the past 2 examples that we've done, we've been creating chains before we're finding our derivatives. For the next 2 examples, we're going to be using a formula that I showed you a couple slides ago. So just to refresh your memory, if we have y is equal to a function raised to the power of p, then when we take the derivative, we're going to bring that exponent p down, multiply by our original function. Our new power will be 1 less, but we do need to multiply by the derivative of that original function. So for example 3, we have f of x is equal to 2x plus 1 to the power of 7. So when I'm finding my derivative, f prime of x, it's going to equal 7. So I'm bringing my exponent down. I'm keeping my original function the same. My new exponent will be 1 less, so a 6. And then I need to multiply by the derivative of that function. So in this case, a 2. Now I don't need to expand this all out. Anything to the power 6 is going to be crazy, but I am just going to tidy it up and multiply that 7 and that 2 and get 14 times 2x plus 1 to the 6. Our last example says f of x is equal to x times 3x minus 2 all to the power of 10. Now, instead of using the chain rule and the product rule, a few of you have noticed that there's some simplifications that can be done in order to make a question easier, and this is one of them. So I'm not going to be doing f prime of x yet. I'm just going to be simplifying f of x. So I'm just going to be multiplying this x through. So a 3x squared minus 2x all to the power of 10. Now I can go ahead and take my derivative. So that 10 is coming down. I'm multiplying by my original function. My new power will be 9, multiplied by the derivative of that original function. So the 6x minus 2. Now, at this point in time, I can go ahead and multiply these together just to tidy it up a little bit. A 60x minus 20 times the 3x squared minus 2x to the power of 9.